All right, this is our fourth kinematics video. We're going to be looking at uniformly accelerated motion, which is something we've kind of already referred to or mentioned a couple times. And the big five kinematics equations. These are really important. AP sort of only includes on their equation sheet or references three of these equations. I do think the other two are important, not because they get used all that frequently, but I think five of them in total helps add to the understanding of how to use them and what they're doing. And occasionally you'll find that one of the two equations that are not on the equation sheet will actually be useful, and you might even want to memorize them. All right, and we're going to get into it. Probably, if I have time, I'd like to do a little bit of problem solving discussion after that, just the as we really get into the meat of uh, Unit 1 problem solving and figure out how we approach these AP questions. Maybe a callback to that, even though we will have talked about it in class already, and there's a video on Schoology as well about problem solving. Okay, so let's talk about uniformly accelerated motion. So for all of our problems, for all the problems we're going to end up dealing with, the acceleration during a given time period will remain constant. So I will make note of that. We will have a constant acceleration in a given time period in our problems. And that's going to be very important when we get to the big five equations because they require that. Now, the one sort of exception to this is you might have a problem where it says your acceleration is 5 meters per second squared for 4 seconds. And then for the next 7 seconds after that, the acceleration is different. It's 8 meters per second squared. So that just means you have to treat those time periods like separately. We'd say we're going to look at those first 4 seconds by themselves and what's happening there, and then we'll go on and look at the last 7 seconds because the acceleration is different for the first 4 seconds than it is for the last 7. So we just need to make sure we're using time periods, looking at time periods, and most of the time, the vast majority of the time in our problems, our acceleration is just going to be some constant value for that, which is good because the big five equations will require that, right? And so the point there is we may still see different accelerations during different time periods, um, but those accelerations will not fluctuate or change during those time periods, even if they're like split up. Okay, so this makes graphing easier. Our graphs of acceleration, velocity, time that we looked at in the last video, those are a lot easier when you don't have to, if you had diagonal lines or curved lines on your acceleration time graphs. That makes your velocity time graphs a lot trickier because then you're going to have curved lines on there too. And then it just adds a level of complication that, although it is realistic and in the real world, we don't just have constant accelerations for long periods of time all that much. Um, yeah, it's what we're going to do is sort of simplify things for ourselves. So it makes graphing easier, and it gives us access to our most important problem solving tools, the big five equations. All right, so uh, these big five equations can only be used, and of course, I should specify here, uniformly accelerated motion is, um, well, I guess I'll just abbreviate it. I was going to write the whole thing. I'm not going to write the whole thing again. Uniformly accelerated motion. Um, there we go. So how do I do this? We'll say that's what it means, and uniformly accelerated motion can be abbreviated that way. Okay, hopefully that makes some amount of sense. Big five equations can only be used with uniformly accelerated motion. We require that if we're using one of these equations, we require that the acceleration remains constant throughout the time period that we're using that equation for. Okay, these equations make use of 5 important kinematics values that we looked at earlier. Now, we might recall that we really only got 4 questions. How far does something go? How fast is it going? Does it speed up, slow down, or change direction? And then how long does it take, like time? So what's going to happen is with velocity, because for most of those, we're going to end up using the vector versions, um, like displacement rather than distance, velocity rather than speed. Time is a scalar, it doesn't have a vector version. So, but with those, we're also going to look at specific instantaneous points in time in terms of velocity, because one of the things we said about velocity was you could have an average velocity over a whole time period, or you could look specifically at exactly this moment in time, this split second. How fast is an object or person moving at that moment in time? So we're going to use those initial and final velocities. So the 5 variables in these equations are as follows. We are going to have displacement. Now I'm going to note this right now. I'm also going to give a reminder in a little bit when we write out all 5 of the equations. I'm going to do displacement, velocity, acceleration in the x direction horizontally. We could just as easily use the y direction. In fact, we will when we have problems where vertically moving objects, like a falling object due to gravity, it's moving vertically. We're going to use things like delta y instead of delta x because if it's not moving horizontally, then we wouldn't use delta x. We would use a delta y because that's a vertical motion. So I'm going to start with these x variables, but really we'll mention that you can have x or y versions of the big 5 equations. Okay, so we've got displacement, which horizontally would be delta x. We're going to look at initial velocity, and I'm going to specify using 2 subscripts, v initial x. So this is the starting velocity in the x direction. We're also going to have v final x. And keep in mind, these are both instantaneous velocities, meaning we're going to look at how fast something was moving right at the beginning of the time period we're looking at, v initial. So that 0 subscript means v initial, the starting velocity at the beginning of the time period at time equals 0. V final, at the end of that time period, how fast is the object or person moving. Acceleration, that is just speeding up, slowing down, or changing direction. So if there is any speeding up, slowing down, or changing direction happening in that horizontal or x direction, then that's that variable. And of course, time. You can put t or delta t, but most of the time they're going to use t in the big 5 equations. And in one of our previous videos, we mentioned that there's really not, for the most part, there's not going to be a difference between t and delta t. It's just a little bit of terminology of how you refer to them. But okay, sweet. So these 5 variables are going to make up our equation. So displacement, initial velocity, final velocity, acceleration, and time. Each equation, each one of the big 5 equations will have 4 of these 5 values or variables in it, with one specific value excluded from each of those equations. This ends up being a really good thing because if let's say that a certain kinematics value doesn't show up in the problem, let's say that time is nowhere to be found. You read a problem, it makes no mention of time whatsoever. It doesn't tell you how long it took. It doesn't ask you to find how long it took for something to move. So there's nothing at all involving time. Well, if if the kinematics value of time doesn't show up in the problem at all, then you should use the big five equation that doesn't have that value in it. Because, well, we'll write them out and we'll talk about with algebra why that benefits us. Okay, so let's write the equations, and then we'll kind of add on some of that reminders about um, picking an equation, which one to use, when would I use it, et cetera, et cetera. Okay, and also just keep in mind we're going to be using subscripts to indicate x and y directions. But we're starting off with one-dimensional motion. We'll talk about that here. So we're going to use x or y subscripts and we're going to be starting with one-dimensional or 1D motion. What that means is horizontal only or vertical only. So the sorts of situations we will see, like a ball rolling across the floor, a car driving on a flat road, a person running on the sidewalk, those would be horizontal motion only, no vertical motion there. Someone throwing a ball straight up in the air, rock falling from the top of a cliff straight downwards, a diver jumping straight down into a pool. Those would be vertical only types of motion. So we're going to begin with that. Eventually, we will get to the point of projectile motion, 2D motion, and both horizontal, vertical at the same time. But we're going to use either x or y subscripts. And when we write these big five equations, we're going to start with the x subscripts because that's sort of our default. Okay, so here they are. Uh, big five. I'm going to talk a tiny bit about where they come from, but for the most part, we're not going to mention too much about, like we call it, like deriving equations or the origin of them. Where did they come from? Do we just believe these equations? Like we talked about it with acceleration, right? We explained, hey, acceleration is a change in velocity over a change in time. That's what it measures, is how much does the velocity change in some amount of time. So the equation makes sense. It's just change in velocity over change in time, and then we get acceleration. Um, so if you want, of course, you can always just trust your physics teacher and say, I believe whatever equations you give me, but I'll do a little explanation of, like, well, how do we know they're true? Where did they come from? And that sort of thing. Okay. So the first one is as follows. It says displacement. Oops. We'll do delta x here equals parentheses initial velocity x. Don't forget your vector signs on the vectors. The final x over 2 multiplied by time is not a vector. Okay, that is the first big five equation. Now, this is actually something we've already seen because average velocity, for one thing, if we were to do a bit of algebra and move some things around, we're gonna leave it as is. We're not gonna move this around in the equation. But if we were to divide both sides by time, it would go away on the right side. Displacement over time is a way to find average velocity. If you take the total displacement that an object has moved in some time divided by the total amount of time, you found the average velocity for that time period. So if we moved the time over, what's left, namely v initial x plus v final x over 2, that would have to be average velocity. And we've even looked at, when we introduced average velocity, that's one of the equations for it. We can find average velocity assuming, as our big five equations require, assuming uniformly accelerated motion, where that acceleration is constant during a time period we're looking at. then we can do v initial plus v final divided by 2 to find the average. So this really just comes from average velocity. It's a slight rearranging of the average velocity equations, either displacement over time or v initial plus v final over 2. Both of those are average velocity. Now, the thing to notice here, of course, is that we are missing acceleration. There is no acceleration anywhere in here. So in parentheses, it could be useful just to make a note, hey, there's no acceleration here. Now, as long as we're dealing with all these subscripts, x subscripts, and initial, final, just to remind you, first of all, that we could do this same equation for vertical motion. All we would do in that case is use delta y instead of delta x, v initial y instead of v initial x, v final y instead of v final x. So you can simply replace all your x subscripts with y subscripts, and now you have a valid equation to use vertically instead of horizontally. We just the basic way we write them is x direction. But you can swap the x's for y's quite easily and use the equation vertically. Okay, cool. Another thing to mention with these, right? In algebra, sometimes we get stuck on, oh, this equation allows me to solve for displacement. Well, yes, it absolutely does. If you have a number for initial velocity, you know that that's 2 meters per second, and you know that your final velocity is 8 meters per second, and you know that your time is 4 seconds. You can do the math. You can plug things in and solve. And you could find your displacement. However, you can just as easily solve for one of the other variables, provided you know the 3 variables besides that one. So we could solve for v initial x. We could find the starting velocity as long as we know displacement, final velocity, and time. We just plug in those values, use some algebra, isolate and solve for v initial x. It's a little more work, but with algebra, we can do that. We can isolate for an unknown variable, provided that we know all the other variables, and we can put numbers or values in for those. So just keep that in mind, right? It looks like this equation solves for displacement, and sure, it does, if you want to, but it also can solve for any of those other variables. If you know 3 of the 4, you can solve for the 4th variable. Okay. Cool. Yeah. So we're writing out these big 5, and just remember, of course, we can use y subscripts instead of x. Just depends what direction our motion is. All right. Big 5 number 2. This says v final equals the initial x plus acceleration times time. Well, there you have it. We can already note what this one is missing. It has no displacement. Delta x, nowhere to be found. So again, in a problem where if the problem statement is telling you about initial and final velocity, and it tells you about time, and it asks you to find acceleration, but there's no displacement anywhere in the problem at all, then number 2 is a great choice for that, because right, you don't need any information whatsoever about displacement to solve with this equation. All you need is, right, if you're solving numerically, we're going to look at other ways to use these equations. We'll look at deriving and doing algebra without putting numbers in. But if you do have some numbers and values that you're given and you're solving for something, right, choose an equation that has in it the things that are in your problem. And if there's something that doesn't show up in your problem, that's actually a very helpful way to choose which equation you're going to use, right? Oh, I don't have displacement anywhere? No problem, because number 2 doesn't need displacement. We'll use the other variables. As far as really quick where this one comes from, it's actually from the acceleration equation. So this is not super crucial knowledge to know, but for those who kind of like the background and like to know where it comes from, if we did a little algebra and we took the initial velocity, v initial x, which is a term all by itself, and we subtracted that from both sides, which is, right, we can do that. We can subtract the same thing from both sides of an equation. We subtract it to move it over to the left, essentially. We'd have v final minus v initial over here, which is the change in velocity, right? The final minus initial is the change. If we then divided both sides by time, moving the time over here to the denominator of the left side, we'd have v final minus v initial, the change in velocity divided by time. Well, that's just equal to acceleration because that's the only thing that would be left over here. So this really is the acceleration equation we looked at when we first introduced what acceleration is. It's just change in velocity, final minus initial, divided by time is equal to acceleration. We just moved some things around and rearranged it to get big five number two. Also, I'll make some notes real quick of what's on the sheet. So this one is on the sheet. The provided equation sheet from AP has three of the five. Number two is one of them. All right, big five number three. This one says displacement equals initial velocity times time plus 1/2 acceleration time squared. Okay. If it helps you to put parentheses around things to keep your terms separate, you can absolutely do that. The AP equation sheet doesn't have it, but if for example, you wanted to go like this, help yourself remember that 1/2 times acceleration times time squared is a term of its own all by itself, then you could do that. That's helpful. Okay, so let's talk a little bit about this one. First of all, there is no final velocity anywhere in the equation, meaning if your problem doesn't have information about final velocity, this is a good one to use, this equation. And we actually use this a lot. This is among the most commonly used, maybe probably the most commonly used out of all the big five. It is on the sheet, which is good because it's used a bunch. Okay, as far as where it comes from, some of you who've taken calculus might already pick up on this, but there's some things here that indicate calculus stuff going on, like the t and t squared. It turns out in calculus, if you start doing integrations, you start getting like higher and higher powers of a certain variable. And same thing, derivatives will do the opposite. So there's some integral derivative stuff here that we're not going to talk about because we're not a calculus-based class. But if you're wondering like where this comes from, you can get into using using derivatives and integrals with things like position or displacement to get to these equations. So that's how you can kind of come up with them or derive them. If you take calculus-based physics, we'll probably talk a little bit more about that. If any of you juniors or below take calc-based physics, Physics C in your senior year or later on, then of course we get more into that. One thing to note on this is the way I've written it here is what I hold to and I firmly believe is the best way to use this equation, but delta x is actually not what shows up on the equation sheet. What shows up on the equation sheet is the beginning of this equation looks like x equals x0 plus ... all the rest of this. So everything that's on the right side, v initial times time plus 1/2 acceleration time squared, all of that would go in right here. So it would be x equals x0 plus all of the stuff on the right side. So it would be the same thing, but the one difference between the equation sheet, which writes it like this, and my preferred version, which is this, the difference is the equation sheet writes it in terms of position, and I like to write it in terms of displacement. Neither is right or wrong, and there might be problems. You could run into a problem where it says an object starts at a position, that would be x0, its starting position. An object starts at a position of 2 meters, and then they give you a bunch of information about how fast it's going when it starts and how long it takes and what the acceleration is. And they ask you to solve for the location where it ends up. Occasionally, the way that it's written on the equation sheet with position could actually be the way to go. I find, however, that much more frequently, the values that we're dealing with in a problem or the information we're given or what we're trying to solve for is way more often including or involving displacement, or that displacement is just a better value to work with. And so these are the same thing because if we subtract x0 from both sides, we would get rid of it over here. And on the left side, we'd end up with x minus x0. That is final position minus initial position. That is just displacement. That is the equation for finding displacement, is the final position your object ends up at minus the initial starting position that your object was located at. So it is really the same thing. Again, neither one's right or wrong, but I do think that writing it involving displacement delta x is, in my mind, more useful for a lot of the problems, given that displacement is a value that we frequently make use of or look at. Okay, number 4. Number 4 is super similar to number 3. It's almost like a spot the differences. I'm sure you can spot them. So we have delta x equals v final x multiplied by time minus 1/2 acceleration time squared. Now this one is not on the equation sheet, but it's definitely not as frequently used. There are a few problems. I think I could probably count on one hand, give or take, like 3 to 5 problems I've ever encountered where this would be a preferred ideal equation to use. Like we really want to use it, and it'd be very helpful to use it. So that makes it tough because it's like, well, do I memorize number 1 and number 4 that are not on the sheet? Number 1, there's like a couple problems I've seen that it's really the best way to go, and it could be harder to do the problem if you don't use Big Five number 1. There's usually some workarounds and other routes, other options. There's more than one way to do a AP Physics problem a lot of the time. But number 4 can be useful, and luckily it's not too hard to memorize number 4 from number 3. The only two differences are use final velocity instead of initial, use a minus instead of a plus before the 1/2 acceleration time squared, and then you have number 4. You can go from number 3 to number 4 pretty easily. So luckily it's not too hard to memorize, and it's a handy one in a couple spots, not super frequent. Number 3 is by far, like, it is used a lot. Final velocity, as you might be picking up from the difference of 3 and 4, final velocity isn't something we see a whole lot of in terms of wanting to know how fast something is going. Usually it's like you drop an object and the final velocity would be right before it hits the ground. Once it hits the ground, it'll be 0 velocity, but then we'd be introducing a different acceleration, which is slowing down as it hits the ground. So falling objects, we're going to look at the acceleration of gravity, and most of the time in those sorts of situations, or just in a lot of our problems, final velocity isn't going to come up a whole lot. Yeah, and for stuff like projectile motion towards the end of the unit, displacement, initial velocity, time, and acceleration are all really big, important values that do get worked with and included. Okay, last one. And again, as far as where it comes from, it's similar to number 3 in that you can get there using some calculus things, and like derivatives and integrals can be helpful for that. Okay, last one, number 5. This says final velocity squared. So I'm going to put some parentheses so we know that we're squaring that, equals initial velocity squared plus 2 times acceleration times displacement. Okay, and that is Big 5, number 5. It has no time anywhere in it. The time variable or value does not show up at all. All right, which of course means if you have a situation where you don't have a way to know what the time is, or time doesn't show up anywhere at all in this situation or problem or thing that you're working on, then number 5 is a good choice because it doesn't require time to work with and solve. Okay. As far as where this one comes from, very interestingly, when we get into Unit 3 later on, there will be energy, and we'll look at changes in kinetic energy. And there's some really cool connections you could make there. I don't know that we'll have we may try to look back at some point if I remember to call back to number Big Five number 5, and we might look at changes in kinetic energy and work, none of which we have to know about right now, but kinetic energy has to do with motion, so like velocity is used in kinetic energy equations, and really you can connect this very closely to kinetic energy based on velocity and work is related to like forces acting and causing accelerations. So and work is all about like displacement as well. Anyways, there's some neat ways you can um, link this equation to work and energy and sort of get to this equation from kinetic energy and work, which is just physics can be like interconnected a lot of times. It's pretty sweet. But we don't have to worry about that now. You don't have to know where it comes from. We just have to be able to use it. And again, algebra is the key here. Sometimes we're plugging in numbers and we're saying the final velocity is 4 meters per second and the acceleration is negative 2 meters per second squared and the displacement is 9 meters. And I'm going to solve for initial velocity and find how fast it was going at the beginning. And then you plug your things in, you solve, you do your algebra, isolate the variable, etc. Other times we'll be deriving where there's not going to be numbers. We're just going to be moving the variables around, doing algebra, manipulating the equation without any numbers in it. And it's a tough thing that most people don't have as much practice with from algebra, but with some practice, I think we'll all get more comfortable with derivation questions. Okay, cool. There they are. Those are the big five equations. They are, again, they're like oh, this one's on the sheet. So it is the third and last on the sheet. 2, 3, and 5 are all on the equation sheet. And they're just very handy. They're useful for, now I tend to, it's a funny thing I've noticed, I really tend to default to using these. There might be problems that a student who really latches on to graphing knowledge and really likes that could solve the problem with graphing skills. A student who maybe has a really solid conceptual grasp of physics and says, I don't need to like look at the equation in this particular instance. I just understand how velocity, acceleration, displacement are at work in this problem. That can be a little dangerous because if you misunderstand or misinterpret or your conceptual understanding is a little bit off, you can get the problem wrong. Versus, if you plug in your math and do it correctly, whether with variables, numbers, or values in an equation, assuming you do the things correctly, it's a lot harder to get that wrong, I think. So I do tend to be more like equation math minded in terms of solving the problems, and a very large amount of problems can be solved just with using these equations in some way. So you'll see me do that a fair amount of the time. Okay. Well, yeah, that's our big five. Now I'm going to add one more thing in here in this video before we call it. Actually, I might add a couple. We'll see. I don't want to make it too long, but projectile motion is a longer topic, so I want to get as much stuff covered here before we get to projectile motion. Okay, so just a brief reminder here, talking about these as our huge, like most common tools, or maybe most beneficial tools for solving problems. When you solve problems, there's some steps that are just good to keep in mind. Whether or not you're using the big five equations, I've found these to be helpful. We've talked about them before, I think. We've seen, even early on in class, I probably referenced them or had you recommended you watch a video on the problem solving steps, but we'll call back to them again because it's a good spot right by the big five where we use them for a lot of problem solving. First one is like, what do I have? What has the problem provided me with? What is the given information? And some of the stuff that you have or that you've been provided is just the context of the problem. Oh, it's a falling object. I know some things about gravity and falling objects and how this works. So just the context of what's happening. Oh, later on we'll do ramps. So this object slides down a ramp. Oh, I know ramps. I know how to do that, right? So the context gives you some clues as to which physics concepts are relevant, which we'll talk about in a second. Second step, what do I need to find? What do I need to find? What is the stated objective or goal of the problem? Um, what are they asking me for? Like, do they want me to create a graph? Do they want me to find what a velocity is at a certain point? Do they want me to determine which of these two objects is moving faster at the end of this time period? What am I being asked for? Because that then once you can put a specific to it, like, oh, I need some information about final velocity, or I'm really concerned about finding out about the displacements of these objects, or I just need to make a graph. I need to make a or select a velocity time graph. Which velocity time graph is correct for this? So it'll be some graphing knowledge. And then the third step, this one is always the hardest because it's easy. It's easy enough to say, kind of figure out what's provided, what do I have, what's given to me in the problem, what do I have to work with. What are they asking me to do? Most of the time, that's not too terribly tricky to find out. Sometimes it's a little weird of like, what exactly are they asking here? But AP questions are like that. And then what tools or equations or knowledge will help me get there? Knowledge will help me get there. So you have this stated objective, you have this goal. You want to get to this, whatever you're trying to find, velocity, acceleration, whatever your goal of the problem is. So, given the information provided and given what you need to find, what am I using for this problem? Is it Big Five number 4? Is it knowledge of velocity time graphs? Is it just knowing how acceleration works? Is it knowing things about gravity or horizontal, vertical motion, vectors? There will be the trigonometry piece. Do I need to use my sines and cosines here with vectors and their components? So there's various tools, skills, equations, knowledge. Some of it is the math, equation, algebra aspect. Some of it is just knowing how certain things work. Or, hey, I happen to know that the slope of a velocity time graph gives you the acceleration. That's a handy piece of knowledge or a tool that I could use in this problem if there's a velocity time graph and I can work with that with the acceleration. So this is a tricky part because it requires you to call upon, right? Physics is unique in the fact that you've got a big toolbox. There's a lot of little, maybe not quite as many terms to memorize as like AP biology, where there's a lot of terms in memorization, but there's still a lot of little bits of knowledge and pieces of things, knowing how something works or knowing a definition of like what is acceleration or what is velocity, etc. Um, and there's a lot of equations, right? There's a lot of things running around. So you've got a big toolbox to choose from. You've got a lot of options. And any given problem is usually not, sometimes it's just one of those things. Like it could be a very simple problem where all you have to do is plug in some things to Big Five number 3 and you solve it. But a lot of times there's more than one piece of knowledge or equation or tool or skill that you need to use. So it's drawing upon all those things to be able to approach and solve a problem, which is tricky. It is tough. And then once you've got that set up, 4 is just show your work. And not only showing your work as you're solving the problem, uh, especially for like an FRQ, free response questions, you really want to show your work and check your work as well, right? You want to go back and you want to look at it. And you want to like just be thorough. There's something that's really tough here in AP Physics, especially with the time limitations they put on some of the questions, right? We're going to start off easy. Like in this unit, we're going to have 5 minutes for each multiple choice question. Should be plenty of time. It's going to get less and less over time, and eventually we'll be to the point where there is a pretty decent time crunch on the time you have for each question. It's hard to be thorough. It's hard to really think it through, evaluate the problem, see what you need to find, correctly apply all these things. Maybe you made a mistake and you tried something, it didn't work, right? So, yeah, like there's time is a big important thing. So be thorough whenever possible. Show your work um, as you solve. And make sure you keep your units and direction. Okay. So units and direction are just important because on your final answer, if it's a vector, you need to have direction. It needs to be the right direction. Keeping track of direction throughout, like which velocity, acceleration are things to the left or right, up or down. Direction is very key. Yeah. So keep your units, of course. We don't want random numbers running around. There's a few things that don't have units on them, but for the most part, all of our values should have a unit of seconds or meters per second squared or whatever it is. Okay, those are the problem solving steps. So just a reminder on those because it's important to be able to solve our problems. Our quizzes and tests are multiple choice or free response problem solving. We're going to do just a couple more things. These are sort of side things. One of them is for vertical motion. It also comes up in two-dimensional motion with projectiles, but for the time being, we're mostly going to apply this just to vertical motion. This is something called free fall. Free fall is a specific term for situations when an object is in the air under the influence of gravity, and specifically under the influence of gravity only. And this is like for its acceleration. Gravity is known for speeding things up or slowing them down. If you throw a ball straight up into the air or throw any object straight up into the air, if you throw it upwards, what's going to happen is right when it leaves your hand, it'll start to slow down because gravity is an acceleration that is directed downwards towards the center of the earth. And if you give an object a velocity going up, it's going to slow down, right? You throw it upwards, it slows down due to gravity. Now, there is some air resistance in there, but we famously like to ignore air resistance. Um, so we'll be doing that pretty consistently throughout our class. Which again, it's like, yeah, it's not the most realistic thing, but air resistance just adds some nice complicated math that we'd rather not be doing. You can do the math with air resistance, but it's a lot more complicated. So we like to say that we treat air resistance as negligible, meaning it's so small that we're just going to ignore it. So we, in these situations, when an object is in the air, we're the vast majority of the time we're going to say, hey, gravity is the only thing influencing this. Gravity is the only acceleration that it experiences. Now, with that, we're going to say under the influence of gravity only, so that the acceleration in the y direction is equal to exactly 9.81 meters per second squared. That is the acceleration of gravity. Well, it fluctuates a little bit. The Earth is not a perfect sphere. If you go to different heights above sea level, if you go to the top of Mount Everest, it varies. You're going to see a little more, a little less acceleration of gravity at different like heights or spots on the Earth. But we're not going to mess around with that. We're just going to say it's 9.8 or 9.81. Actually, AP is going to round to 10. So you could make a note here, or whenever you're doing your problem, AP rounds to 10, which I think is a generous rounding. I don't know about that, but it does make the problems easier. So I guess I can forgive them for it. So it is going to make it easier to work with and solve your problems with 10 as your acceleration in the y direction instead of 9.81. You get to do that. Also note this scenario of free fall, an object is in the air under the influence of gravity. It does not have to be moving downwards to be in free fall. The word fall is a bit deceiving because, yes, fall, we usually think falling downwards, like it's moving down. But if you throw something up in the air and it's moving upwards, it's out of your hand, it's in the air, it's under the influence of gravity, accelerating it. I guess I should actually, uh, here, how am I going to do this? I'll put a negative sign here. But I'll specify that we'll do it over here. You might have seen me do this already at some point. This would be saying that up is positive and right is positive. I mean, the left-right doesn't matter here, but if up is positive and down is negative, gravity is a negative acceleration because gravity, of course, accelerates things downwards, meaning that they slow down if they're moving up and they speed up if they're moving downwards. Okay. Anyway, that's being a little picky on direction, but it is a vector, so I'm going to make sure my direction's in there whenever possible. Okay, so that's just free fall. Is objects in the air, gravity is affecting them. Gravity is a vertical acceleration in the y direction. That acceleration ay equals, well, 10. So we're going to use 10 with AP. Okay. We'll do one last thing here, which is relative motion with equations. It's not too tricky here, so we'll do a couple examples, and there's not a lot of these in AP questions. Relative motion. So let's say that we've got a person that's jogging, and someone who's driving in a car is observing them. So both those people are moving with respect to the surface of the Earth. So if an object is moving, like this person that's running, I guess they're a person, not an object, but in physics terms, of course, object could mean anything. So if an object is moving, like a person out for a jog, but the observer, the person in the car that's looking at them, um, maybe you're yelling at your friend to run faster while you're driving your car, and they're mad at you because they're running. And I hate running, but maybe some of you enjoy it. Um, it's good for me, but it just is painful. All right. So an object is moving, but the observer is also moving relative to the ground. Okay, so like a person's running, the person in the car is the observer, and they're moving relative to the ground. Uh, we can use vector addition or subtraction to determine relative velocity. Okay, so relative velocity is just um, this is just the velocity as observed. So our observer is not standing still on the surface of the Earth. So what velocity do they observe the person running with? We could draw our little example real quick here. So there's our person running. Let's say they're moving at a velocity of, I don't know. I'm a slow runner, so I'll say 1.5 meters per second. And the car is driving with the person inside it. Don't worry, they're not going to run them over. I just don't have that much space to can't draw in and out of the board. So my perspective is a little bit off. But there's the car with the person inside driving. And we'll say that they're moving at much higher velocity. We'll say 6. Now they're both moving to the right, so we could say they're both positive velocities. We could call it V1 and V2. So V1 is our observer, V2 is our runner. And to the person in the car, if we want to find out that relative velocity, we'd just say that relative velocity is equal to V2 minus V1. Or another way to write this is you could say it's the velocity of like the object or whatever is being observed minus the velocity of the observer. So it's the velocity of, again, whatever object or person is we are observing and saying, how fast is that person going? Which is funny here, right? Because V2 minus V1, 1.5 minus 6 gives you a negative number, which at first is like, wait, what? Negative? Wouldn't that mean like backwards or to the left? But the person isn't running to the left. Well, no, they're not. But relative to the car, if the car were actually the thing that was standing still, because the car is going faster than the person, from the point of view and the reference frame of the driver of the car, or the person in the car, that runner is going to go like backwards past them, right? In reality, you in the car are passing the runner, but to you sitting in the car, you could make the argument that, well, I'm just sitting still. The universe revolves around me, right? Me and my car. And this person went backwards past me. They went in the negative or left direction. So it does get a little weird with relative velocity, because even though both of them are moving forward, to the person in the car, the velocity of the person is actually negative or to the left. But yeah, that's how you find it. There's not a ton of problems like this, but when relative motion comes up, you can take the velocity of the object minus the velocity of the observer and find what the relative velocity is. Okay. Cool. Well, we are going to leave it there. We'll get into, well, in class, we should be doing a fair amount of one-dimensional problem solving. We're working with graphs by this point, so we've got plenty of stuff to occupy our problem-solving homework and questions we work on. But the last thing that we'll end up getting to in Unit 1 is projectile motion. So, yeah, we'll be doing that. We'll talk about two-dimensional motion and projectiles. All right, we're going to call it there and see you in class and see you for the next video. Don't forget to leave some questions. So if there's anything that's like confusing, weird, if it's my first attempt at these videos. And so anything that felt unexplained or I didn't explain it in a way that you could understand, or there's just a question or like concern about anything, post question. There's that Padlet to put anonymous questions or comments. And yeah, that way we can clarify things and improve things and make sure people are feeling good about the topics we've covered. Alrighty. Thanks, folks.